Electronic Quantum Resources, or ElQuRes, is a QuantERA collaboration between two experimental labs in Paris and Braunschweig and two theory groups in Lyon and Riga. And we are studying how fundamental quantum properties of electricity in semiconductor chips can be turned into building blocks of future technology.
In our lab at ENS in Paris, we're doing experimental physics and we're working on two-dimensional system of electrons. We are studying them at low temperature and under high magnetic field and trying to figure out what happens in this kind of system. Basically, the magnetic field will create one-dimensional edge channels that appear at the edge of the sample, and then trying to conduct electrons through these channels. We're trying to study them and behaving in this very peculiar behavior. And then we're trying to confine them into what we call edge magnetoplasmon resonators and trying to study the physical properties and trying to study the emergence of new particles in this kind of system in condensed matter physics.
An important dimension of quantum technology is the science of measurement. We have our colleagues at the National Metrology Institute of Germany, PTB, developing a general purpose method to quantify the quantum state of carriers of electrical currents. Here in this animation, you show how the image of the electronic wave function emerges gradually by adding more and more slices. The method is called tomography, and it's directly related to the idea of reconstructing inner workings of a body from two-dimensional slices. In this case, the slices are measurements of quantum mechanically incompatible variables, and we want to know what part of the information is really quantum and what is the limitation of our instruments. We hope that such a toolbox will be useful in several applications of electronic resources. Part of the challenge for the theory of electronic quantum resources is that when electrons move in mass, they become a quantum field. And instead of the simple one particle wave duality, we need to confront the duality between bosonic and fermionic representations of such a stream of chiral electrons. And this is where our theory partners from ENS Lyon group come in. They develop sophisticated technique and they experimentally relevant models to capture the exact quantum elements which allow to distinguish, control, and measure the state of quantum electrical current.
Science cannot happen in isolation, and for a young researcher like me, it means a lot. I can meet a lot of great experts from different countries there, have discussion, and learn from their experience. It also makes Latvia an open and welcoming place for research. International collabs can inspire new ideas and future discoveries.
What excites me personally as a theory group leader here at the University of Latvia is that the ideas and models we've developed over the years about single electron counting, where we maximize the precision of the particle nature of electron, can be turned into answering the question, what is the ultimate limit for the wave packets that can be generated from dynamical quantum dots? We now believe that we can translate the microscopic parameters of the electron confinement into the shapes and the minimal sizes of wave packets that can be used as fast probes of local on-chip electrical signals. And being able to validate our models in real metrologically relevant experiments is the collaboration dimension which makes QuantERA so worthwhile for our group.
So I'm a young researcher at the University of Latvia. In this project we study what are the device parameters that set the quantum resolution limits of wave packets. In this project I enjoy meeting new people and sharing my own research with them. And finally, I'm glad to be part of something bigger on a European scale, so that together we can make a bigger impact.
We hope that the scientific results of ElQuRes will help define entirely new types of building blocks for future technology. For example, can a flying qubit store its information in a resonator? Or what's the optimal set of quantum pixels to use with most sensitive voltage probes? These practical technologies are being pushed for within other European collaborations that we keep close ties with. For example, the project ElQuRes tries to build a quantum computer based on ballistic electrons. Project EIQuRes from European Metrology Partnership works on the most precise calibration of single electron sources for practical sensor applications. And I think together this network of projects spans the right talent from the fundamental science to the best engineering and finding use cases where such cutting-edge research can have meaningful impact in everyday life.